Not yet.
Not yet.
Oh, I can hear myself here. How about now? Is it good?
We will know in 1 minute.
Okay.
Every street is a runway. And everybody plays that.
Hello.
That's early probably for people, 8 a.m., right? Morning. Okay.
Are you gonna stand here and speak into this, or are you gonna take it with you?
I mean, I can take it with me if they're going to turn this on.
Having a hard time figuring
Okay.
out what to turn on here, so I don't
Okay.
want to mess any.
Oh, I see. Oh, no.
This
So you-
camera issue.
It's okay. Yeah. Oh, that's fine.
Yes, they had it on.
Oh, yesterday they had this one?
Well, they had it on for the opening, and then they turned it off because it was glare when we actually had the opening.
Okay. Just the
remark.
opening? Okay.
It was
What?
off. It was off. It
Okay,
was just
okay.
on when we walked in.
Oh, I see. And then it was off all day,
Then it was
basically?
off all
Oh,
day,
okay. Yeah.
except for they use for the middle section.
Okay.
So they do use it, but they said.
Interesting. Yeah. Yeah. I like it on actually because people are sitting in the front now. They're going to have to look to the right and left, right? In the middle. Okay, sure. Yeah, one more time, maybe.
Good morning, folks. We're ready to get started. The keynote, please make your way to me. Does it in Korean?
Yeah, that could be easier, you know. Yeah, yeah.
Just always work.
Yeah, yeah.
I'm plugging the wrong cable.
Yeah. Should be easy though. I mean,
I know.
right? You know, not the
Crazy
most
setup
exactly.
there.
Not the most complicated place in the world. Yeah.
The setup they have there is pretty
Is it?
complex.
Okay,
They
yeah.
look at like this
Sure, sure, yeah. That's
TV studio.
audio and yeah, yeah. They have all these knobs, right, to turn, yeah.
The camera feed.
Yeah, yeah. Hey. Let's see.
Good morning. Please be seated.
Anjun's coming. Yeah, okay. That's fine.
Yeah, they were just telling us.
That's why they turned it off yesterday, probably. You know, I don't know. Zoom solves all of these issues, you know. Everybody can distributed manner watch.
Yeah.
Exactly. Yeah, go ahead whenever. I'll follow you.
Let's get started. Please be seated. Gonna get started with today's keynote. It's a great pleasure to introduce today's speaker, who really needs no introduction, but I'll do my best. Onur is a professor of computer science at ETH Zurich. His research interests are in computer architecture, computing systems, hardware security, memory and storage systems, and bioinformatics. His group's major focus is on designing fundamentally energy efficient, high performance and robust computing systems. His research has had broad impact on industry. The techniques that his group developed have been adopted in microprocessors, memory systems, and storage systems used by billions of people. He's also influenced the research of countless research groups in industry and academia. He was recognized by numerous awards. I encourage you to look at his bio for the complete list. Just to mention a few: multiple Test of Time awards, the Sigurd Maurice Wilkes Award, and many others. He's also a fellow of both ACM and IEEE. So let's give Onur a warm welcome.
Thank you very much, Radu, for the invitation, and thank you for this nice introduction. It's great to be here back in Seoul. I think last time I was here was like 10 years ago, although I used to come a lot more regularly. Hopefully that'll change from now on as well. I don't know if you can see the slides, but it's coming. Do I need to do anything? Yeah, it's already connected over there.
Turn on the mirror mode?
Mirror mode. Maybe. Okay, I think we got it. Yeah. I guess my first lesson of the day is the importance of testing beforehand. This was not tested beforehand, even though we asked for it. And it's not the organizer's fault. It's somehow it didn't get tested. And now I have to look at far away to see the slides. But hopefully people who are here will not get some eye problem. Okay, I titled this keynote, Can We Do Better? I'm going to talk about both technical and non-technical aspects. And here's a summary. I think this is a philosophy. Essentially, can we do better is the philosophy to improve things, in my opinion. It's a philosophy that moves the needle. And we should be embracing this much more in everything we do. And I also like being a nonconformist, and I'd like to question and deconstruct the status quo a little bit. And I'd like to apply this philosophy today to the memory problem, which we've been working on for many years, and also a little bit about enabling better and more efficient innovation, which I believe we're having a lot of issues with today, not just in the computer architecture community, but science in general. And maybe sleeping well, but we don't have time to talk about that, I think. Let's see. So a summary of the memory problem. This is one slide summary. You can go to sleep. I know it's early if you get everything out of this. Computing is a huge memory problem today. People have argued with nice papers in the past that computing is an energy problem. I would argue that most of that energy problem, and that paper also shows that most of that energy problem is due to memory. And memory is really responsible for many things: performance bottlenecks, energy consumption, robustness problems, monetary cost, hardware real estate. And this problem is becoming much worse with more data-intensive workloads. And I believe we can change it. We can solve it by changing the paradigm, by designing much more memory-centric systems. And in this talk, I'm going to show you two areas where we can do better. We can do better in technology scaling by designing memory to be much more autonomous compared to a processor. Today, memory needs to do things that the processor dictates. Why not have the memory do things on its own, as opposed to being controlled by the processor all the time? And the second part is memory can perform computation, and this can enable much better application and system scaling. And I call this a paradigm shift. This is not going to happen overnight because we're very ingrained in our processor-centric thinking. If you think about the paradigms in science, they all took many, many years. If you think about Copernican revolution, for example, it took 200 years to solidify. It didn't end with Copernicus. It required people like Brahe, Kepler, Galileo, and eventually Newton to come to an end. And if you think about it, this such an ingrained paradigm is very difficult to change. And I believe we're at that point in processor-centric systems. I keep people asking, When are we going to move to processing in memory? Well, we don't know, because it requires a whole lot of change, and it's really a paradigm. It's a new way of thinking. Okay, so let me jump into it. Basically, the problem is today computing is bottlenecked by data, and data is really key for many applications. You heard a lot of talks, and there are many sessions on AI, but AI is not the only thing in the world. There are many other applications that are important, like genomics. And clearly, memory and compute requirements of these applications are increasing exponentially, especially in the AI domain, because that's where the push is happening, at least at the very, very cutting edge today, at very large scales. But also, genomics is a very important application, and we should not forget that there are other important applications in the world. So we should not dedicate all of our conference sessions to AI only. The problem is data access is really a major performance energy bottleneck, and our current design principles waste a lot of energy because we keep moving data all around in our system because of the processor-memory dichotomy. And we also lose a lot of performance because of this, but we recognize this a lot, and we try to complicate our systems to overcome that performance loss. We add many, many levels of caching and buffering in our systems, many, many levels of prefetching, very high bandwidth memories to improve parallelism, to tolerate the latency effects of data movement, many levels of multi-threading. So essentially, our out-of-order execution in many general purpose processors, we complicate our hardware and software a lot to actually overcome the performance loss. And when these techniques work, they may be okay. They don't always work. Sometimes work, they do. When they don't work, they actually compound the energy waste that we have. They actually increase the latency in many cases. So basically, we're in this vicious cycle today. We have a processor-centric mindset and design paradigm. To overcome that, we actually complicate our systems a lot. And as a result, maybe we keep wasting energy. Okay, so I already said a lot of this. All data gets processed in the processor at great system cost, and processor can be essentially anything that we design that is logic today: CPUs, GPUs, FPGAs, whatever you want to add over there. So I'd like to take a critical view on this. This is my picture that I drew in XFIG in 2008 when I first wrote my NSF proposal while I was at Carnegie Mellon. And I like this picture because it's kind of nice. It's still the same, the system today. The cores may have changed. Essentially, we have a distributed system of cores or heterogeneous accelerators in our system. And those are the computation units. This is a single node we're looking at. Everything else in the single node is dedicated to storing and moving data. Caches interconnect, other caches, other interconnects, other caches, other interconnects, storage, etc. So most of our system is dedicated to storing and moving data. If you do the calculations, 95% of the hardware real estate. I'd like to take the critical view, and a critical view actually could be taken with a blank slate. And my good representation of a blank slate today is a 10-year-old kid. If you were a 10-year-old kid, how would you design a system? Because a 10-year-old kid doesn't have vested interest, is not making money. And maybe they will make the right decision at some point that's good for energy or something like that. So give this picture to a 10-year-old kid. This is an experiment to do, perhaps, for some of you. And ask the question, I'm dedicating almost all my hardware real estate to memory and storage. Should this be my problem? They will hopefully tell you that you're putting all your effort there. That shouldn't be your problem. But unfortunately, our systems are still bottlenecked by memory and storage. So that was hardware real estate. Let's look at performance. There are many, many studies. I'll pick one study from Google 10 years ago, a beautiful paper, ISCA 2015. Essentially, they analyzed all of their data center workloads, and they found out that most of the time in all of their data center workloads is spent on waiting for data on a cutting-edge processor from memory. The processor is doing what it's supposed to be doing only 10 to 20% of the time, which is finishing instructions. Again, take the perspective of a 10-year-old kid. Ask the question, I designed the system. The goal of the system is to finish instructions. It's doing what it's supposed to be doing only 10% of the time. It's a good design. They would be honest with you and they would say, go design something else. Okay, that was performance. Let's take a look at energy. Energy is even worse. Again, I borrowed a slide from Bill Daly from about 10 years ago. The numbers have changed, but the relatives have not changed as much. A complicated arithmetic operation, 64-bit double precision floating point operation, 20 picojoules, and memory access, 16 nanojoules. That's 800x difference. If you optimize, maybe you'll get to 100, 150, 200x. Still, there's a huge difference. The question is, does it really make sense to move the data, all of the data, to the processor to actually optimize for energy? This is actually not a dogma. It's really an optimization problem. And Memory has very nice slides showing that you need to actually reuse the data many times, thousands of times, to overcome the energy differential of memory access versus compute. And the question is, do we have that levels of reuse? Can we get to that levels of reuse in our systems? In many workloads, that's not the case. In some workloads, that may be the case. And this problem becomes worse if you actually make computation cheaper, which is what we want to do and what we are doing. If you have a 32-bit arithmetic operation, integer operation, the disparity is 6400x. If you go to 1 bit, 2 bits, that disparity will increase. And we're not even talking about storage yet. Storage, add another 10x over there, so 64,000x. Now go back to your 10-year-old kid. They would be going crazy. Why are you moving this data? Spending 64,000x to do 1x. Just keep it there. Okay, so we tried to understand the energy cost, along with many other people in the community, of moving data. And we did a lot of studies with Google especially. And in this work, in ASPLOS 2018, we showed that more than 60% of the total system energy is really spent on data movement, on important applications like TensorFlow, inference, Chrome browser, video encoding and decoding. We more recently repeated the study on edge TPU accelerators, and we found out that more than 90% of the total system energy is spent on memory in large machine learning models. And when you accelerate computation, memory becomes a bigger bottleneck. So actually, if you have a very good accelerator, your memory becomes a bigger bottleneck. So you need to actually design your memory system much better for that accelerator compared to a more general purpose system. And if you're interested, the paper has a lot of data. At the time, the larger models were LSTMs and transducers, and you can see that the memory access, the energy is dominated by off-chip interconnect and DRAM. So basically, we have a fundamental problem, and we should recognize the fundamental problems and try to solve them. Processing of data is performed far away from the data. So how do we solve it fundamentally? We could keep patching it, no question about that. And that's what we've been doing for many years. And that effort should continue. But I would also argue that a bigger effort maybe should be done on changing the paradigm, exploring new paradigms that reduce this problem. These paradigms will not happen overnight, as I said, but it's worthwhile to investigate them for that we can have a better place in the longer run so that we can stop patching things. So we want to enable computation with minimal data movement. We want to compute where it makes sense, where data resides. And sometimes that is actually the processor itself, but many times that's not. And we want to make computing architectures more data-centric. And you can see that there are many places where we can do computation. Today, we're restricting ourselves to this SRAM-dominated chiplet. And there's a lot of darkness in the system, DRAM, storage, sensors, that cannot do computation on the data, even though they store the data or they ingest the data. So in the rest of the talk, I'm going to look at memory as an accelerator. There's another paradigm where you can actually think of every agent in the system, including memory, sensors, etc., as an independent agent that can do everything. That's more of a distributed system. I'm not going to go there. We're going to look at the accelerator model because we know how to design accelerators, and we've been doing so much of processor-centric accelerators. Why not have memory-centric accelerators as well? Even with that accelerator model, there are a lot of challenges. Basically, if we store data in our memory, I'm going to focus a lot on main memory, a little bit of storage maybe, but mostly main memory, DRAM. If you want to ask DRAM, can you execute this function, instruction, or application for me? You need to change the interfaces, essentially. You need to also design the DRAM or memory to be compute capable, memory controllers to communicate information. You need to design the processor perhaps differently once you have computation capability. You need to design the communication units carefully so that you can communicate nicely. You need to change the hardware and the software interfaces. You need to change the system software, compilers, and languages to actually take advantage of this efficiently and also easily for many people in the world, because many people in the world don't want to actually even know how computation happens, right? That's happening in our world today. And you actually need to change your algorithms to match the hardware as well. And my favorite over here is really the theoretical foundations. If you think about the theory of computation, that's very processor-centric. We count operations to get to the big O notation, big theta notation, but maybe we should not be doing just that. We should probably be looking at data movement, right? If that's actually important. So we don't have a data-centric theory of computation today. So I should also say that this is not a new idea. There are a lot of smart people who walk this earth, and they exist in architecture community also. These are the papers that I found, the earliest papers from 1960s, Kautz, beautiful paper, processing near memory. Another one from Harold Stone, who has a beautiful textbook on computer architecture. How many people have read that textbook, by the way? I'm curious. Harold Stone's textbook. Okay, I see some hands. That's great. When I ask this question to my students, nobody is aware of Harold Stone. But it's good to, I think, be aware a little bit. Okay, but these people have actually looked at processing near memory. The question is, what is different today? Basically, I would argue that today we have nowhere to escape. I already gave you a lot of data from application and systems. There's a lot more that could be given. We have a huge data access bottleneck. Energy and power are huge bottlenecks, and data movement energy dominates computation energy. And today we want performance, energy, and sustainability all at the same time. We don't want to trade off between these because things are getting much worse going into the future. And we can improve all of these metrics by minimizing data movement. We also have huge problems with main memory technology at the device and technology levels, and I'm going to start with that actually in this talk. Memory technology scaling is not going well. For example, there are problems like RowHammer, and these scaling issues demand intelligence in memory, and DRAM manufacturers are already putting computation inside the DRAM chips to solve these issues. So if you already have computation inside the memory chips to solve these issues, why not add more computation inside the memory chips to do acceleration and other things? And I believe emerging technologies are important, and they can enable new functions in memory. So we're squeezed in the middle. So I will also interleave this talk with some suggestions, because I think we're going to get to some other issues, maybe some hard issues for the community. But I believe to truly solve fundamental problems, we need to defy business as usual. Business as usual is easy, and relatively easy, I should say, even though there are a lot of difficulties over there as well. But business as usual doesn't change the paradigm. So you don't need to resolve a lot of the issues that we're going to talk about. But without defying that, you cannot really get to something much better and much bigger, in my opinion. And a good mindset is, what would a smart 10-year-old kid do? I also like Robert Frost, so I'll read this poem over here. We want to take the path less traveled. And he says in 1915, when the US civilization was actually probably at higher points, I shall be telling this with a sigh, somewhere ages and ages hence, two roads diverged in a wood, and I took the one less traveled by, and that has made all the difference. Okay, take that as an analogy. He may be telling something else, actually, in that poem. Okay, again, US civilization at its height in the 1800s. People should be nonconformists, I think. Okay, let me jump into memory technology scaling after that lighthearted thing. So we've been doing a lot of studies using real DRAM chips, building a lot of infrastructure to understand the technology scaling issues that are happening with DRAM and flash. I'm going to talk about DRAM in this particular talk. We built a lot of FPGA-based infrastructures. This is our lab at ETH. We keep building up. You can see a lot of FPGAs. We want to actually put more there so that we can understand the capabilities as well as downsides of existing DRAM chips. This is the infrastructure at CMU where we did a lot of RowHammer experiments. And the bottom right one over here is the first infrastructure that we built in 2011. We open sourced these infrastructures, SoftMC, which was published at HPCA, and then DRAM Bender, which was not published at a top conference because it was rejected multiple times. And we acknowledge all of those efforts. But it's still been useful, and people actually here have been using it with nice results in Korea. Okay, I'll tell you the story of a couple of things. With this sort of infrastructure, you can study a lot of issues. RowHammer is one issue that we've extensively studied. So the problem with RowHammer is that you can induce bit flips in existing DRAM chips under regular operational conditions by keeping on activating a single row. The idea is if you activate one row, you apply high voltage to the word line, and this application disturbs cells around it, which means that some vulnerable cells lose charge a little bit because of the cells are too close to each other and the cells are too small, they have too little charge. Now, if you keep doing this repeatedly, meaning pre-charge the array, apply low voltage, and then apply high voltage, low voltage, high voltage, low voltage, high voltage, low voltage, activate pre-charge, activate pre-charge, activate pre-charge, and DRAM, it turns out some vulnerable cells in physically nearby rows lose charge little by little and eventually deplete their charge. So you corrupt the cells. This is silent data corruption. It should not be happening, but it's happening because cells are too small and cells are too close to each other. And we've demonstrated that essentially all DRAM chips today are vulnerable to this problem because cells are very small. This problem has been getting worse. We did our initial experiments in 2012. The paper was published in 2014. I'll tell you a story about that also. But basically, as cells become smaller and closer to each other, the number of activations you need to induce a bit flip reduces. And it's reduced by at least 10x in the course of the last 10 years or so, which means that to mitigate this issue, you need to be a lot more careful. If if a single row activation causes a bit flip, what do? Is at the end of DRAM scaling, you cannot really activate a cell, right? If 100 activations cause a bit flip, what do? Real applications do that. Okay, this is the original RowHammer paper that we wrote. And security community took actually to the start because they were looking for bit flips to actually easily inducible bit flips to take over a system. And they've demonstrated that you can read data that you don't have access to. You can break out of virtual machine sandboxes. You can corrupt important data. You can render ML inference useless. There are actually papers in the recent Unix security that show that you can do that in GPUs with GDDR6, for example. I'm waiting for the HBM paper. It should be there, but it's not easy to reverse engineer all of these things. You can steal secret data like cryptographic keys or ML model parameters. Basically, you can do anything that you don't want. So we have written a lot of papers. I'm not going to bore you with a lot of papers. We've written a retrospective. This is relatively old. And more recently, we wrote a short retrospective at 50 years of ISCA. So this is not the only problem. The problems are getting worse. I'm going to give you a couple of examples. At the same ISCA in 2023, we introduced RowPress, which is essentially a different read disturbance mechanism than RowHammer. In RowHammer, if you want to induce bit flips, you keep activating a row as frequently as possible, as allowed by the standard. In RowPress, you don't activate the row that frequently. You keep the row open for a while. And the fact that you keep the row open by itself induces disturbance in adjacent rows. And this is a very different mechanism, as we have shown in our paper at the system level. And we showed that you can reduce the number of activations to induce a bit flip by 1 to 2 orders of magnitude. And it affects essentially all manufacturers. You can see real results. And we open source all of our code. A lot of people have actually replicated and shown that RowPress is a problem in real systems. So why am I telling you all of this? Basically, to solve this sort of problem, if this were a RowHammer talk, I would give you potentially 10 different solutions. But really the solution, in my opinion, is to design intelligent controllers. Because this sort of problems are going to get worse and worse as technology scales. And you're not going to be able to find a low-cost solution unless you move to some other materials, which is going to be not so easy. Even 3D DRAM today is not easy, for example. We're trying, but 3D meaning not 3D die stack DRAM, truly 3D DRAM with cells on the 3D. So you would like intelligent controllers to fix these issues. So we've argued for this many years. This is one of the earliest papers that we were invited to write at the International Memory Workshop. More recently, those guys have invited us to write another paper. We basically said that we need to do more of this and more urgently, let's say. And the good news is, over the course of 10 years, industry, even though they have been reluctant initially, they have been, let's say, moving towards the right place slowly and slowly. This is a paper that was published by SK Hynix at ISSCC 2023. This is the first paper that publicly acknowledges the RowHammer problem for a major DRAM manufacturer. And basically proposed a solution, which is along the lines of what we've argued for many years, which is an intelligent controller. It may or may not be the best solution. I'm not going to discuss that right now in this talk. But it is a solution in the right direction, meaning inside the DRAM chip, or it could be in the memory controller, but they did it inside the DRAM chip, they introduce a controller, essentially, an intelligent controller. Every row has some metadata. This metadata is a counter, activation counter. And this controller, every time a row is activated, you increment the counter. And if the number of activations to a row is greater than some threshold, you take some mitigating action, refresh some adjacent row. They don't tell you exactly how they do it, so there's still some security by obscurity aspect, which we don't like necessarily. But this is a solution that's being adopted in industry. And there are a lot of course, how to configure this solution that's not so easy, which I'm not going to get into in this talk. And this is standardized by JEDEC. All DRAM chips going forward are going to implement this. And this is actually, for some industry people said that this is probably the biggest change in that has happened to DRAM in the last 20 years or so. Of course, the question is, are solutions good? This is a solution. It's solving a problem. You don't need to be a 10-year-old kid to figure out what that problem is. But you also don't need to be a 10-year-old kid to figure out that this is a bad solution to the problem it's trying to solve. So we try to evaluate these solutions. We have written a paper at DRAMSec and extended. So there are better solutions, basically, we believe. They will come at a cost that is higher than what we have, but you don't have to trade off performance as much. I'm not going to talk about the specifics of the solutions, but essentially they require more and more intelligent controllers and perhaps modifications with the DRAM chips going into the future. Okay, so the question always is basically, can we do better? So I believe we can. So the solutions so far assume memory is still a slave to a processor. And that's one of the problems with the JetX solution that is out there. Memory cannot do things independently by itself. For example, if the memory cannot really refresh the rows before bits get flipped, the JetX solution has very high penalty. And that actually leads to very high performance overheads. So what we have argued in this paper is to better partition the duties of DRAM and the controller. As opposed to controlling, dictating everything DRAM does, why not give some freedom to DRAM? DRAM should be able to do some autonomous operations by itself. If it wants to do RowHammer protection on a small subarray, just do it. And when the memory controller actually asks something from that subarray, DRAM says, no, I'm not going to satisfy your request. Try again. That's the idea, basically. If you actually do this, this requires very little change, a small pin that you need to add to a DRAM chip. This is a huge change in DRAM. In my opinion, this is a very little change in the grand scheme of things, and this sort of idea should be encouraged going into the future. This way, you can partition the work much better. Memory controller does what it's good at, what the processor designers are good at, and the DRAM chip does what it is good at, what the DRAM designers are good at optimizing it for. For example, they can optimize for refresh. The memory controller doesn't need to say refresh, 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 refresh. The DRAM itself can do refresh alone. It can do RowHammer protection. I believe this can partition the work nicely. This is a more principled approach. It does disrupt the status quo. No question about that, because it does change how the memory controller is partitioned, because today the memory controller is not partitioned. It's in the domain of processor designers. So we have shown in the paper that you can do better refresh, better RowHammer protection, better memory scrubbing without changing the interface. You could keep updating what you do inside DRAM, and the interface stays constant. Today, if you want to change the interface, it takes a multi-year effort, and you have to convince 390 plus companies in the JetX committee, which is very, very difficult to do. That's why many, many good ideas in DRAM space have been declined. Okay, so that's self-managing DRAM. I have a little story about this. It took us 7 iterations to get this paper published. If I were in JetX, this could have been easier to publish. I'm not in JetX for many reasons, but basically we thank all the reviewers for this. But I will raise the issue: are the reviewers asking the right questions? Are we really trying to move the needle in research? Are we being worse than JetX? These are some of the comments we received. What are some business impediments? The idea is commercially unattractive. I will not read everything. These slides will be available. You can take a look at it. I like this one. Radical idea. I don't consider it radical, but okay. Complex and requires co-design, likely will remain as an academic work. Reject. But the good news is research-oriented reviewers also exist, and they do see the value. The problem is I don't think our review processes are tailored towards people who see their value to actually push a paper in. And I believe we need to do more in our review process so that people who see the value in a paper can actually get it in, as opposed to a majority vote. Okay, this was accepted after 3.5 years. It takes a lot of resilience for a student to stay that way. And this causes, in my opinion, mental health problems in our community. And we should be a lot more careful about that. Okay, so basically defying business as usual is not easy, as you can see. But I would say that do not be shackled by standards and reviewers. And sometimes reviewers are too shackled by what the industry is doing, what the standards are. That's business as usual. As researchers, I think we should be avoiding business as usual, defying business as usual. That's how you can make the big strides. If Copernicus actually wanted business as usual, he wouldn't have developed his theories. Do you want to be Copernicus, or do you want to be like the flat earthers we have in many places? Okay, basically a suggestion to researchers: you got to be resilient, because this system is not going to change that easily, although we will try, I believe. And there's more to come. There's actually more to come in both what I'm going to describe, but also in DRAM. Essentially, there's still a whole lot we don't know about DRAM. And this is really fascinating to me. DRAM was invented in the 1960s by Bob Denard. First patent in 1968. This is a 60-year-old technology. And we're discovering new things. Aging, for example. There's not enough data. There's not enough understanding of aging. And this actually keeps me up at night. Sleeping well is not easy with this, because if we actually use these DRAMs, cutting edge technology in space under harsh conditions, even not so harsh conditions, safety critical conditions, will this work? I don't believe it will work very well. So we analyze this a little bit and we publish papers. More recently in HPCA this year, we have discovered that with the read disturbance threshold of a row, the number of activations you need to induce a bit flip changes randomly and unpredictably over time, meaning that you cannot really predict this. There's a quantum-like effect that causes this randomness. We don't know the reasons for this, actually, underlying device-level reasons. There are no device-level papers that describe this. We're discovering these things at the system-level testing. That happened with RowPress also. There were no device-level papers that talked about the RowPress problem at the device level, circuit level. Normally, how innovation happens is you build some materials, you build some devices, you understand the properties, and then you build some systems, right? Here we have a technology that's 60 years old, and we're still discovering things at the system level because we find some error problems, and there's no explanation at the device level. Device level papers come later. This is really fascinating to me. So that's variable read disturbance. At this conference, Ismail will present something that may become much worse into the future. It's not a big problem currently, but the scaling trends show, according to our results, that a single row activation flips bits across 3 DRAM subarrays, and it's very difficult to protect against this. So we should be actually publishing work earlier than it becomes a problem in real systems. And in another work at ISCA, we have shown that if you're doing processing using DRAM, which I'm going to talk about, RowHammer becomes much worse, actually. So there are a lot of interactions in these things. Okay, you may say that, okay, this is 60-year-old technology. What about less older technology? I think all of the technologies have their problems. I'm not going to go into that. But some of these technologies off the bat require intelligent controllers. That's why we keep building our laboratory for understanding memory. And I will say that despite all of the, let's say, negative comments that you receive, researchers should still follow their passion. They should not get derailed by naysayers. And infrastructure building is really important. We actually invested a lot into this infrastructure since 2011. We're investing even more today. And I think that can enable some new discoveries. But this requires hard work. Infrastructure is something that not many people appreciate, unfortunately. And when you sometimes build infrastructure, people find bugs and write papers about it. Instead of writing papers about it, which may be wrong, you can actually come and talk to people who actually build the infrastructure. So this requires a lot of resilience also. Okay, let me just quickly give you, if this was a RowHammer talk, I would talk about a lot of RowHammer things. RowHammer is actually very interesting today in many communities. I'll flip through these slides. This is the RowPress explanation that came after the RowPress paper at the device community. And finally, there are serious changes in standards. And Girai has written a PhD thesis on this. This is one of the state-of-the-art theses. There's more coming up. This year, there were redisturbance sessions at HPCA, ASPLOS, ISCA. We had a DRAM sec. You can find it on YouTube. Usenix Security has 7 papers. I was actually surprised to see that. I thought RowHammer would die by now, but now we have 7 papers because it's a technology scaling problem. They're actually quite interesting papers over here. And we have some redisturbance papers at Micro as well. Although one of them is classified under superconducting systems. So maybe there's something that we need to figure out, superconducting and RowHammer. Now, let me give you a little bit of history because I think there are a lot of students over here. RowHammer sounds very interesting, I think. This is the original paper. It led to a large body of work, large industrial efforts, and the work continues, and I believe it is going to continue. But initially, it was dismissed by reviewers. It was rejected from Micro 2013. We could have published it, let's say, 1 year, calendar year earlier. And these are the reviews that we received from Micro. You can see that the reviews are very divergent. There are a couple of people who really like it. There are 4 people who really hate it, let's say. And let's take a look at why. So one person says security is not realistic. Essentially, this doesn't happen with real workloads. And we did not show it with real workloads, although RowHammer in the field was discovered when running a real workload before we did our studies. But this reviewer clearly didn't know that. They said security is not important. If you show me a real workload does this, come back and publish. Should that be our bar for publication? Okay, we basically say security is just as real. Okay, did you verify it with DRAM manufacturers? Have you ever talked to a DRAM manufacturer? Sorry, we're in the DRAM land over here, but we did actually talk to DRAM manufacturers, but we cannot write everything in the paper. No architectural content. This is another reviewer. Essentially, may not spur on future work. And they say this is an excellent test methodology paper. So go and publish it somewhere else. I think this is very closed-minded. We should really not do that to any of our students. Our community can generally only observe, not correct such problems. Well, I think hindsight shows that. Okay, let's see. This is a very well-known novelty, 0. The good news is in ISCA, we got better reviews, even though the paper did not fundamentally improve. The problem is the same. We did test more chips. We improved the evaluation a little bit. Writing is probably better. Yes, no question about that. Did it require an iteration to get this published? That's a good question. Despite all of these, there are still 2 reviews, which is actually very interesting. One of them says, this is already done on YouTube. There's a 3-minute YouTube video which dedicates 10 seconds to talk about RowHammer. It doesn't exist anymore, gone. I tried to find it yesterday night. I couldn't find it. Basically, this is very well known, already done on YouTube. I actually know that video. That video was done by Mark Lantane in the MEMCON conference after our first paper was submitted and rejected, October 2013. It's a 10-second video that talks about testing for, let's say, activate precharge issues in the DRAM. Okay, and then this is very interesting. I find this very interesting. Basically, the relevance of paper to the ISCA is low. You should submit it at most at ITC or DSN. Those are not good conferences. We're ISCA people here. I'm not even sure that you can publish it over there. Okay, there's a rebuttal. I'm going to skip that. Another review, RowHammer appears to be well known and solutions have already been proposed by industry to address the issue, which is not wrong. We actually talked about the patents that Intel filed to solve this issue in our paper. Okay, basically a testing and reliability venue, go away from ISCA. My preference would be to see a much shorter characterization section. That's the value of the paper, I would argue. Okay, there's rebuttals that I'm not going to talk about. So basically, as evaluators of scientific work, can we do better? These are my suggestions that I presented. If you have seen me given a talk 6 years ago at ISCA 2019, I presented this. And I will go over this a little bit more today because I think we have an even bigger problem today compared to 6 years ago. Basically, let's just be fair. We do not know it all. Nobody knows it all. We do not know the past, present, and definitely not the future. We do not, because of that, we should be open-minded. Because of that and other reasons, we should be accepting of diverse research methods. There's no single way of doing research or writing papers. And this is something that people get stuck at. If my paper, characterization paper, goes to someone who doesn't value characterization, it's easy to get it rejected. If my idea paper, big idea paper, goes to someone who wants everything implemented, it gets rejected, right? And actually, in ASPLOS 2015, Guri Soy, I was on a panel with him. He said exactly the same thing, basically. If the purpose of the paper doesn't match the mindset of the reviewer, you're done. So we should be much more careful. We should be constructive, not destructive, and we should accept more, in my opinion. We won't have much to lose from accepting more unless there's something really seriously wrong. And I think there's a double standard issue. There are double standards, and people are not even aware of their biases. We should really suppress those biases. Basically, we should not block or delay progress for non-reasons. And this is actually a very fun reading from Wall Street Journal, among all places. It's still not bad. Don't fault the fact that it was published at Wall Street Journal. Could Einstein get published today? I doubt it. With this climate, in architecture community at least, they're not going to get published. In some other community, maybe, I don't know. But there's a lot of bureaucracy that has gone into science today. Actually, Einstein, there's a story about Einstein. He went to the US and he sent the paper to a journal. And then he got reviews. And then he was furious. He said, I didn't send my paper to you to be reviewed. I sent it to be published. But of course, being a smart person, he addressed some of the review comments and he sent it somewhere else. Okay, so I will recommend one book. How many people know this book? Since not many people know about Harold Stone. Okay, there are more people know about this Raj Jain book. It's a beautiful book, The Art of Computer Systems Performance Analysis. Among many, many other things that are beautiful in this book, I like this one. This is basically rat holes. I think in reviews, we're getting into a lot of rat holes today. And this is actually very nice because it gives you the size of the rattles, workload, metrics, configuration, detail. I'm going to read it. Even if the performance analysis correctly done and presented, it may not be enough to persuade your audience, potentially reviewers, decision makers. The list shown in box 10.2, next one, is a compilation of reasons for rejection heard at various performance analysis presentations. You can use this list by presenting it immediately and pointing out that the reason for rejection is not new and the analysis deserves more consideration. Also, the list is helpful in getting the competing proposal rejected. That's, of course, tongue-in-cheek. So you can see that the most common, and any analysis can be rejected simply on the grounds that the problem needs more analysis. This is endless, right? When do you be satisfied, basically? And we see this in many reviews, in Shepard's, etc. The second most common reason for rejection of endless analysis and endless debate is the workload. Since workloads are always based on the past measurements, their applicability to the current or future environments can always be questioned. I'll have a story about that later on. Okay, I'm not going to read the rest, but you can look at this cartoon. And this is 26 reasons that he has for reasons for not accepting a paper, let's say, from my context. And the last one is my favorite. Why change? It's working okay. This goes against the can we do better philosophy. But this is a beautiful book. I'd recommend people to look at it. Yeah. Okay, let me give you some more story. These are some reviews that we got after RowHammer paper was published. IEEE micro top picks. And you can read, I poked around a bit and DRAM vendors have already solved this problem. RowHammering appears to be a known problem. Okay, I seem to remember that during the presentation at ISCA, it was pointed out that DRAM manufacturers have already fixed the problem. So where's the novelty and long-term impact? A little bit aggressive. Okay, I was not convinced that this paper will be cited in the future, blah, blah, that opened a brand new research area. I don't like looking at citations in general, but a delayed rebuttal is fitting in this case. Okay, so I'll repeat my suggestions to the reviewers because they predicted the future in this particular case, as opposed to evaluating the merits of the paper. Okay, so I believe we need to fix this reviewer accountability problem. So what is the problem? In my opinion, the problem is multiple things. Closed-mindedness, no question about that. But the reviewers have no accountability. Right? And we all know, given the current situation in the world, what happens if people don't have accountability. So just like main memory needs intelligent controllers, research community needs accountable and open-minded reviewers. And this is a fundamental problem, in my opinion. If there's no accountability, you will keep patching and patching and patching and patching and patching existing system, increasing the load on the system, making it worse and worse for everyone, authors, reviewers, PC chairs, and you will not solve the fundamental problem. And everybody will go crazy. Okay, so if we want to patch the system a little bit, at least what we could do is accept papers liked a lot by some reviewers. Ignore the negatives. Don't do things based on majority voting. A majority agreement should not be necessary. Avoid increasing negativity and bias. For example, don't anti-champion papers, please. We already have enough negativity in the system. And my litmus test in all of these is, what is our goal? Why are we doing what we do, right? This is not a competition. Sometimes I get weird comments from reviewers saying, oh, you played with the font sizes, formatting a little bit. This is not fair to others. Come on. What is our goal here? Our goal is really to advance science, right? That's what the conferences should be about. The conferences are not about competition, right? I mean, I'm saying this because I've written a lot of papers, but my goal in writing papers is not writing papers. My goal is really to advance science and have impact, right? And that should be our thinking going forward. And not everyone needs to agree on acceptance of a paper to achieve that goal. Okay, so basically that was for the reviewers, but as students and producers of science, can we also do better? I think we can. Basically, we should not get derailed by naysayers and toxic comments. You can control what you can control, right? You cannot control what someone says about your work unless there's an issue in your work or there's an issue in your writing. Be resilient. Focus on learning and scholarship. That's the main thing you can focus on because some things you cannot change. In the end, I think the quality of the work defines impact. And I believe if you work hard, you can enable that and you can make a great or good impact on the world. And people should not be derailed if they want to make that impact. I will suggest this reading by Richard Tamming, you and your research. Probably many of you have read this one. He has a lot of good advice to researchers. Okay, let me switch gears a little bit, talk about processing near and using memory. I'm not going to talk about processing near memory. So processing in memory has two types, in my opinion. Processing, you have logic and memory. You put logic closer to memory. That's processing near memory. That's already happening in industry. It requires more work to happen, not easy, etc. But it's a bit shorter term. Processing using memory says, forget about logic. We have memory. We're going to use the memory as a computational device. We're going to use the analog operational properties of that memory to do computation. So I'm going to talk about that. I'm going to skip these slides on processing near memory, even though there are a lot of interesting stories, including some work that we've done with Seoul National University here. This paper was rejected from Micro because of me, because I was on the program committee and I could only have 2 papers accepted. And these poor guys couldn't have the paper accepted in 2014. So I apologize, but that's another example of bad rules that we have had in the community. Okay, and now it's actually a short retrospective. Okay, there are many examples that I'm not going to talk about. I'm going to talk about processing using memory, essentially focusing on processing using DRAM. And we can do a lot with DRAM. Essentially, we can support block bitwise copying, initialization, all bitwise functions, random number generation, complex computation using lookup tables. Most of these are at low cost. We're going to use the analog computational capability. And the primitive is activating multiple rows in sequence or concurrently performs data movement or computation. That's the idea. And it turns out even in commodity off-the-shelf DRAM chips, you can do it by violating the timing parameters. You don't have to change the DRAM chip. You don't have to change the interface. Okay, I'm going to go through this relatively quickly, but let's take a look at copying. If you want to copy a source page, this white page, to the gray page that are very close in memory, let's say, what do we do today? We have to go through the processor. Again, take the hat of a 10-year-old kid. Give this to a 10-year-old kid, say, I'm moving data all the way to the processor just to do this copy, even though these two things are in the same subarray, maybe, in DRAM. They will tell you, just do this, right? That's what we want, basically. And this turns out to be another rejected idea from ISCA 2012. Okay, or sorry, 2013. But actually, if you do that, you get low latency and low energy for copying data. And the best case, that's at least so far, we know that this is the best case. If you want to copy a source row to a destination row, and they happen to be in the same subarray, you activate the source row, which brings the data into the sense amplifiers, and you activate the destination row, which actually connects the destination row to the sense amplifiers by deactivating the source row. And the data that's strong in the sense amplifiers get copied to the destination row. So by using the sense amplifiers as a buffer, you copy the source row to the destination row. We showed that this is negligible hardware cost if you want to do it reliably. And in our paper in 2013, Micro, we showed that you can reduce latency and energy significantly. Okay, that's real cool. So how do you do a computation? So if you concurrently activate 3 rows, that performs computation in DRAM. I'm showing you one cell in each row over here, ABC. Imagine this happening in millions of cells in DRAM. You concurrently activate ABC. What happens is, based on charge sharing principles, if at least 2 of these cells are charged, you get the charge state at the end. If at least 2 of these cells are discharged, you get the discharge state at the end, meaning this is a bitwise majority function. So a circuit theory states that this is bitwise majority, which is essentially bitwise OR and bitwise AND if you set C accordingly. Now, you don't have bitwise NOT, but you actually have bitwise NOT if you actually activate one row. The complement of the row, complement of the data is actually on the other side of the subarray. You just need to supply it. So you have a functionally complete bulk bitwise Boolean engine in DRAM. That's the idea. So it actually can be adapted to any workload, right? It's not just workloads that use bulk bitwise operations, although there are some workloads that actually use bulk bitwise operations in the world, like databases, web search engines, DNA sequence mapping, encryption, set operations, etc. And we have shown that you can actually improve performance significantly by mapping a bit viewing database, which was developed at the University of Wisconsin, at Jignesh Patel's group. You can improve performance energy significantly. So that's Ambit, basically. Let me give you a brief history. Essentially, this was rejected 4 times. Okay, maybe 5 times. I have a typo over there. I need to correct that. Okay. Let me count. 1, 2, 3, 4, 5. That should have been 5. Sorry. So this is what the acknowledgements over here actually serve as history that corrects my own wrong writing as well, as you can see. Okay, maybe it was rejected 4 times and was accepted in the end. So you can generalize this. So you can actually implement any operation. And you can actually make it more flexible by modifying DRAM. If you want to actually have smaller bit width operations, You make DRAM more finer grained, enable access to each mat separately. This is fine-grained DRAM. There's many works on this topic. This way, you can actually execute some things on one mat and some other things on another mat. That's now a multiple instruction, multiple data model, as opposed to single instruction, multiple data model. So you can actually have a bulk bitwise engine in DRAM that's much more capable, much more flexible. So we have our own fine-grained DRAM design that I'm not going to talk about. Of course, you need to add some things for aggregation and reduction operations internally. And you can map an existing compiler, LLVM compiler, to ease programmability so that you can actually discover this parallelism in the workloads and map them nicely to the DRAM mats. And that's what my student Geraldo did in his thesis. I'm not going to talk about that, but you can actually do this completely transparently to the programmer with a lot of work and effort. And in the end, we get significant performance and energy improvements compared to existing devices. I'll not go through this in detail, but the improvements are real because these are a limited set of workloads where we could actually extract that parallelism really, really well. This is not the entire workloads in the world. Okay, so you can also have dynamic precision and flexible arithmetic. I also have an interesting story over here. This was rejected from math class after satisfying all revision requirements. Basically, the reviewer said, it's all good, but we still don't like it. Okay, the good news is actually existing DRAM chips are actually already quite capable. So we published our papers, and then there's this nice paper from Princeton that showed using our soft-MC infrastructure that if you actually violate the DRAM timing parameters, you can do row clone and some of the bitwise operations. We built on their infrastructure to actually have an end-to-end design where you could map an application. The application does page copy, or true random number generation. That gets shipped to the memory controller, and the memory controller violates the timing parameters, does the page copy or true random number generation, and returns the result or an acknowledgement, and the application can continue executing on the RISC-V processor. This way, you can evaluate end-to-end without changing the DRAM, real techniques where you can do copy and random number generation. If people are interested, you can develop it. It's a lot of work to develop, and architecture community doesn't like publishing it, so it was published at TACO. Well, top architecture conferences. TACO is great. I have no problem with TACO, but I think we should be more accepting of diverse kinds of work. And this is real results. You can actually improve throughput and copy and initialization throughput significantly on real workloads. That's more on PyDRAM. More recently, at last HPCA, we have shown that you can actually do a lot of other things as well as DSN. Essentially, commercial off-the-shelf DRAM chips are capable of, by violating the timing parameters, you can copy one row into up to 31 other rows with almost perfect reliability. You can perform the NOT operation, and you can perform AND, NAND, OR, and NOR operations. I'll give you the basic ideas. So the basic idea is row clone, you activate the source row, you activate the destination row. If you violate the activate timing parameter, it turns out you activate the destination row while the source row is activated. As a result, you can do this copying in real DRAM chip. In multi-row copy, we have another way of activating, another way of violating the timing parameters that enables the activation of many rows, 32 rows, let's say. And if you actually do that, you can copy one row to 31 other rows, including itself. That's the idea. So NOT operation I'm going to skip, but I'm going to give you the more general version. If you can manipulate the bit line voltage, you can express a wide variety of functions using the simultaneous multi-row activation capability. So I'm showing you 4 cells, 2 in the top subarray and 2 in the bottom subarray. Let's assume that you had the primitive to concurrently activate all 4. You can do that by violating the timing parameters. What happens is, in circuit theory, the sense amplifier would compare the average voltage of A and B to the average voltage of X and Y. Now, if you're smart enough to actually, or if you're capable enough and smart enough to actually put the right values in the reference subarray, I will call, you can perform a function in the compute subarray based on the values that you have in the reference subarray. So if the values that you have in the top 2 cells are VDD and VDD over 2, and there's another beautiful paper from Princeton that shows how to do VDD over 2 in DRAM that we have replicated and we've shown, the average voltage here is 3 VDD over 4. In the compute subarray, if you want to get 1 in the compute subarray, your average voltage should be greater than 3 VDD over 4. So if X and Y, if and only if, assuming you have VDD 0, VDD over 2 as the only values in your alphabet, if and only if X and Y are 1, you get the 1 in the compute subarray. That's an AND function. And by definition, you get the NAND on the other side of the subarray. And OR is left as an exercise for the reader. It's a good exam question for freshmen. Okay, so there's a lot more, but I'm not going to talk about that. So we tested all of these using our infrastructure in our laboratory. And we were able to induce this, especially in SK Hynix chips. Well, copying is done in all of the chips, but some manufacturers don't allow exploration of their DRAM chips for whatever reason. So if you want to copy, actually, all manufacturers allow it as far as we can see, and you get almost perfect reliability. You can almost use it in real systems. And NAND, OR, and NOR are not as reliable, but they're not that bad, depending on how many inputs you have. In some cases, more than 94% reliability. I don't believe this is enough, but there are papers that are actually building on these works to actually do low-bit LLM inference, for example, and map it to real DRAM and actually have a full prototype using real DRAM using FPGAs. I think this is fascinating. That's not our goal. Our goal is to actually design the DRAM, change the DRAM as a robust computational substrate. And these results actually show that maybe even if you do nothing, you actually get these functions. What happens if you do something? You can do better. So this is a multi-row copy. This is functionally complete DRAM. And I'll give you a little bit of history about Ambit before we get to the end. So this was rejected 4 times. 4 is right, I think. This was disruptive. It spans algorithms to circuits. It was rejected from 4 conferences. Now let's see a little bit why. It was called Buddy RAM. We changed the name over time. On archive, you can find Buddy RAM. There's ISCA, Micro, HPCA, ISCA. Okay, ISCA. Very clever novel idea, great potential, speed up energy gains, probably won't ever be built. Reject. And you can see more detail, very interesting and novel, but this will never get implemented because the reviewer has a crystal ball. I wish I had that. And this is not a scientific review, in my opinion. Okay, another review, again, same thing, basically. Unlikely that something like this will be adopted. I'm not convinced any DRAM manufacturer will consider modifying DRAM. Some DRAM manufacturers are interested in this at this point. I will not name them. Architectural innovation is not high. It suits better ISSCC, but you need to fabricate the chip. I wonder if this reviewer fabricated the DRAM chip before. I would love to. Please. Okay. This is very interesting. I've never seen real-world program profiles with hot functions or instructions that are bitwise operations. I would recommend Hacker's Delight. It's a beautiful book. But there's another aspect of this, which is maybe not today. What if you had the substrate? 20 years down the road, maybe you change your algorithms to be block bitwise. So stop innovation because you have never seen a function. But I have seen system profiles that show non-trivial time zeroing pages. Suggest retooling your work to support page zeroing and evaluating that with a full system simulation. Take a look at blah, blah. You might be surprised at the possible impact. Yes, that was the row clone paper we wrote a few years ago. It's interesting, right? Unfortunately, we cannot communicate this easily with the reviewers, and the reviewer has no accountability. As a result, reject. Okay, I know that a lot of people empathize with this, a lot of students. You're not alone. Okay, so basically summary says, it's a great idea, uniformly positive, but they're concerned about the feasibility of the design, meaning DRAM manufacturers will not implement it. Okay, so finally it was accepted at Micro 2017 after 2.5 years of effort or so. So basically some questions to ponder here. Do all research ideas need to be commercially viable? I would argue no. If yes, when? Should it be immediately? How can one predict the future? Right. So maybe no, and giving some leeway to these ideas is a good idea. Can a non-viable idea become viable if circumstances and technology changes? Or even if it never becomes viable, can it inspire something else that could be useful if you publish it? Does a paper have to solve all problems with an idea? Or can it do just enough to enable fast and efficient progress? Are all reviews bias-free? Or are there hidden or visible conflict of interests? And we cannot really answer this question, in my opinion, in all honesty. So why don't we accept more papers? What do we lose from being more positive and accepting? So I think our litmus test should be to efficiently enable advanced scientific endeavor. So it's good for the reviewers to ask, is my review scientific? Does it rely on a crystal ball? Or do I demand too much from the authors? Okay, I'm almost at the end. There are a lot of other things we can do with commodity memories that I'm not going to talk about. But this is fascinating, and we keep finding more and more. And you can find a lot more in our archive paper that is almost 100 pages today, but it's already out of date, let's say. Okay, so adoption is a big issue. I'm not going to talk about it, but Arvind, who passed away last year, gave a beautiful keynote talk at ISCA in 2005. How many people were there? Probably many people, I can see. One of his major conclusions, it was a beautiful talk. One of his major conclusions was we should have worked a lot more on software in data flow so that it can get it adopted. Data flow had a lot of impact, no question about that, but it could have had maybe more impact if adoption issues were solved easily or earlier. And I think there's a lot of adoption issues in changing the paradigm to something like processing in memory. But I think we can do better with a memory-centric mindset, and we can get there step by step. And one of our recent theses by Geraldo, who I mentioned earlier, covers the entire stack, hardware and software. And these things become very difficult to publish if you actually cover the entire stack. Okay, let me conclude. So I think changing a paradigm is not easy. I've already discussed the Copernican revolution. It took 200 years to, let's say, definitively prove that the sun does not revolve around the Earth, and it's the other way around. And also other things, of course, related to that. Does the Earth revolve around itself is another interesting thing. I'm not saying this is at the same scale, but the fact that minds are ingrained so badly in the processor-centric paradigm requires time. It will not happen overnight, but it can enable many benefits. Not all of them are quantifiable or predictable. In a paper, you cannot show that processing in memory is better than everything out there. There is a long history of things that has happened in GPUs, CPUs. You cannot beat all of them in one paper. But also, we need to change the publishing paradigm that we're very stuck at today. We need accountability. We need more positivity. I believe we need review education, bias training, and we should accept more. And our litmus test, in my opinion, should be advancing science quickly and efficiently. And I believe archive and format-free publication is important because I also see many people dealing with formatting issues, changing rules, etc. This drives students crazy, in my opinion, and they're right. They should not be dealing with formatting, in my opinion. They should be focusing on doing the science and writing it up. If a paper is half a page long, whatever, half a page long, right? The goal is to do the science, not satisfy a particular format. We don't need to be bureaucratic about it. This can happen overnight, I think. But this requires will, and this requires a big mindset change. But I think we have a lot more exciting research to do and efficiently enable. And I think we need to be thinking about how we can enable it better. And I think this can help us. And we can also imitate this maybe to do better processing in memory, because this thing doesn't distinguish between computation, communication, and storage as much. So I'll acknowledge many people who funded this sort of research. Most importantly, I'll acknowledge my students. Some of them are here, some of them are presenting papers. And you can see some pictures of them over here. Thank you, and I'm happy to take questions.
Thank you very much, Onur. Questions, please?
Hey, Onur. Great talk. And so from someone who doesn't do PIM, right? The processing in memory, to me, ultimately is a communications problem. And if the data needs to interact with something far away, let's say you have terabytes of data, and then this piece of data need to interact with another piece of data. Right now, the processor is the communicator, right? So if you need the processor to communicate, you may as well just grab the data, right? So fundamentally, how are you going to architect the communication in such a way that the processor can get out of the way?
Yeah. So thank you, Wenmei. That's a great question. And this is actually a problem that multiple works have been tackling in the community. And we do need to solve that problem. I don't have an easy answer at this point. This is another of the research things that people should investigate. One of the issues that we have with memory today, if you look at a DRAM chip, even locally, there's very little communication, right? The DRAM chip, the interconnect, is really designed for moving the data out and in. It's not designed to do computation. So we really need to rethink how we design the chip so that we can communicate across different parts of the chip. And after that, we need to really think how we communicate across different chips that are more memory-centric without going through the processor. So I think people are looking into it going forward. 3D stacking and emerging technologies will help, no question about that. But I think we need to be a lot more disruptive in how we actually rethink memory. Connectivity is a big problem.
Maybe a couple more questions. This name affiliation.
Great talk, Onur. Isha from Microsoft. I had a question about the accept more part of the talk. I know that a lot of people take a lot of pride in getting their papers accepted in conferences with like really small acceptance rates. So how do we reconcile with that? Like we have things like computer architecture letters, but as you know, it's not as popular to submit to things where the acceptance rate does not matter. So how do we reconcile?
Yeah, I mean, that's a good question. That the reward system is not necessarily set up for accepting more. I agree with that. But again, I think the reward system is also wrong, I would say, because it really is not really rewarding advancing science, right? I think basically it doesn't pass the litmus test that I proposed. The litmus test should be advancing science as opposed to putting artificial limits on what fraction of the papers. Maybe we should have designed a better reward system. And I think this requires a rethinking, which is we're not going to solve right now. And I don't necessarily have all of the ideas. And I don't suggest that my ideas are the right ones. But maybe we should really be having a workshop or workshops on this topic to figure out what is a better way of rewarding papers. So let me give you one system. Everybody puts things on archive. And over time, you evaluate things. Maybe 2 to 3 years later, you figure out with some committees or whatever, some bureaucracy, which papers are good and which papers are bad. I don't want to call good or bad, but which papers are, let's say, should be awarded some fraction if that's the goal, right? So I think that relieves a lot of the scientific advancement parts from the reward system. And I think we need to decouple the reward system from how we advance science. Right now, they're too coupled.
Thanks for the great slide. We won't keep going from past time. So and I talk a lot about this one. Let me just try to define what DRAM manufacturer do. They're doing their job. You're doing your job. Right? The DRAM design has to be optimized highly for cost. And I believe you have engaged with DRAM manufacturers a lot. Let me ask this question in front of this gigantic audience. If you're to serve a CEO for one of the DRAM manufacturers for a day, and you can change only one thing, any actual thing, what would you like to do?
Oh, okay. I'll change the mindset. So, okay. I think the problem is, yes, no question, DRAM has been optimized for cost. But that's not necessarily a fundamental thing, right? It's been optimized for cost because of the processor-centric paradigm that we have had. And we don't, in my opinion, DRAM manufacturers are doing what they're doing in a great way. The issue is they know how to do only that thing. Their business model is optimized for that. They don't know a better business model. So maybe if I were there, and I'm not the right person to do this, I would hire someone that would change that business model so that they can actually be less free of that cost constraint.
Thank you very much, Onur.
Thank you.
We're out of time. Let's thank the speaker again.
Thank you. Oh, thanks. Yeah, yeah thanks.
I think everybody needed to hear this.
Okay, that's great to hear. Yeah, I think.
Us.
Oh yeah, sure, all of us. Yeah, all of us. Sorry. Thank you. Yeah. Okay. Right. Yeah.